Oh, whoa, what's up, fam squad? Welcome to the Chucky Has YouTube channel, and today we'll be counting down the top 10 Fortnite funny moments. Our favorite Fortnite gamers are great at the game they play, but sometimes they make some silly little gaffes. I have compiled the best ones and will be presenting them to you all. But first, a word from our sponsor. Here is a fact. Tums is the best antacid. Now, I hear you in the audience saying, Caleb, that is an opinion. You have no scientific basis. But that's where you're wrong. You want science? I'll give you science. To understand why Tums is the best antacid, first it must be understood what acids and bases are. The understanding of acids and bases starts with the understanding of solutions. There are two parts of a solution. There is the solvent, most often a liquid, that a solute is dissolved into. So, for example, when salt is dissolved into water, water is the solvent and salt is the solute. This is called an aqueous solution because water is the solvent. Water is especially good at dissolving solutes because of the differing electronegativities of its atoms. Oxygen is a much larger atom than hydrogen is because oxygen has 8 protons while hydrogen only has 1. This means that oxygen needs a lot more electrons to be considered neutrally charged, so it pulls electrons in much tighter to itself. So while these hydrogen and oxygen do share electrons, the oxygen pulls it in much closer, which makes it partially negative charged, while hydrogen has the electrons further away, which makes it partially positive charged. The imbalanced charges is what makes things dissolve in water. Take hydrochloric acid, abbreviated as HCl, for example. In this molecule, the chlorine is negatively charged while the hydrogen is positively charged. When placed in water, the positively charged parts of the water, being the hydrogen, surround the chlorine, while the negatively charged parts of the water, being the oxygen, surround that hydrogen atom, which ultimately splits them up. Molarity can be used to measure the concentration of these atoms within the solution. In the top example here, imagine that this box represents 10 liters of solution, and each pair of molecules here represents 1 mole of hydrochloric acid. Molarity is the number of moles per liter. So in this first box, there are 10 liters and 1 mole. So 1 mole divided by 10 liters is 0.1, meaning that in this box, the molarity of hydrochloric acid is 0.1. In the bottom box here, imagine that this is still 10 liters, but this time there are 3 moles of hydrochloric acid, which means in this case there are 3 moles per 10 liters, or 0.3 molarity hydrochloric acid. The pH of a solution is highly tied to that solution's molarity. pH stands for the power of hydrogen. Determining the pH of a solution is directly based on the concentration of positively charged hydrogen ions within the solution. Water is the simplest example of this. While water consists mostly of H2O, there is a possibility that a highly electronegative oxygen atom will steal another water molecule's hydrogen atom, which turns H2O and H2O into H3O and OH. This H3O is called hydronium. Now, this hydronium appears very rarely within water. It has a molarity of 10 to the negative 7. To turn this into a pH value is really quite simple. All you need to do is take the negative log of that concentration and it will give the pH. So in this case, the negative log of 10 to the negative 7th is pH 7. And because that is the pH of water, that is the most neutral pH. By calculating pH through negative log of the concentration of hydrogen ions, solutions with lower pH values will have more hydrogen. This can be seen in the difference between a 0.1 molar hydronium solution versus a 0.001 molar hydronium solution. Obviously, the higher number means a more concentrated solution. The negative log of this one is 1, while the negative log of 0.001 is 3. The pH of 1 is more concentrated with hydrogen than the pH of 3. Any solution with a pH less than 7 will be considered acidic, while any solution with a pH greater than 7 will be considered basic. The idea of pH can be applied outside of water. A common acid, as explained before, is hydrochloric acid. When dissolved into water, it breaks apart into its two individual ions, the hydrogen ion and the chlorine ion. Hydrochloric acid will contribute 1 mole of hydrogen for every 1 mole of hydrochloric acid added. This means that the molarity of the hydrochloric acid will be the exact same as the molarity of the hydrogen ion. In a solution with, let's say, a 2.3 times 10 to the negative 4 molarity of hydrochloric acid, the pH will just be the negative log of that concentration, which is 3.63. A solution has a pH, but also a pOH, and these two values are direct opposites. This is because the hydroxide, which is the OH, will neutralize a hydrogen, by combining together to create water. This means that acidic solutions will have greater concentrations of this H+ ion, while basic solutions will have greater concentrations of this OH ion. The process of determining the pOH of a solution is very similar to finding its pH. In water, sodium hydroxide will be split into the two ions sodium and hydroxide. This means that for every mole of sodium hydroxide added, 1 mole of hydroxide is added. Therefore, in a solution with a concentration of 4.6 times 10 to the negative 5 for sodium hydroxide, all you need to do is take the negative log of that, and the pOH is 4.34. However, as pH and pOH are opposites, knowing one can yield the value for the other. The pH scale goes from 0 to 14, so if a solution has a pH of 4, then it would have a pOH of 14 minus 4, which is 10. The idea of neutralization is very important. When acids are added to bases, they will inherently neutralize each other. The hydrogen will combine with the hydroxide to create water, while the other atoms will combine together to make a salt. An example of this is hydrochloric acid plus sodium hydroxide. In this case, the hydrogen and hydroxide of each molecule combine to make water, while the sodium and the chlorine combine to make table salt. And this is pretty consistent for all combinations of acids and bases. They will combine to make water and a salt. When given the molarity and volume of a base and the volume of an acid with an unknown molarity, that molarity can be determined. So in this example, we know the molarity of the sodium hydroxide is 0.1. The volume is 150 milliliters, and for the acid, we know that the volume is 100 milliliters, but we do not know the molarity, and we will be calculating that. The first step is to convert the molarity and volume of the base into moles. This can be done rather simply because molarity is just moles over volume. So if you multiply each side by volume, it just cancels out to be moles. This can be seen here. 0.1 molarity is multiplied by 0.15 liters to find that there are 0.015 moles of sodium hydroxide. Next, the amount of moles that will be canceled out by the sodium hydroxide can be found by multiplying the number of moles of sodium hydroxide by the molar ratio of hydrochloric acid and sodium hydroxide in the reaction, which, as can be seen here, is 1 to 1. The number of moles of sodium hydroxide can be converted into moles of hydrochloric acid, and this is really quite simple. 0.015 moles times 1 over 1 yields 0.015 moles of hydrochloric acid. The final step is to determine the molarity of the solution by dividing this number of moles by the volume, which is 0.100 liters, and that gives a molarity for the hydrochloric acid of 0.15. However, not all neutralization reactions are perfectly balanced. Here, the molarity and volume of both solutions are given. They both have the same volume, however, the acid is more concentrated. This means that there is more acid than there is base. So, when the two combine, there will be leftover acid. The question is, how much? The first step to figure this out is to convert the given data into the number of moles for both solutions. This follows the same process of multiplying the volume by the molarity to find the number of moles. So for hydrochloric acid, there is a 0.03 molarity times 0.1 liters, which gives 0.003 moles. For the sodium hydroxide, there is a 0.02 molarity times a 0.1 liters, which gives 0.002 moles. The number of moles of acid that the sodium hydroxide will cancel out can then be calculated by taking the number of moles of sodium hydroxide and multiplying by that molar ratio, which is 1 to 1, to find that 0.002 moles of sodium hydroxide will cancel out 0.002 moles of hydrochloric acid. Then, the number of moles of hydrochloric acid that there are, subtract the number of moles that will be canceled out, gives the number of moles that will be left over after the two solutions combine, which is 0.001 moles of hydrochloric acid. Finally, this can be converted into a molarity by dividing that number of moles by the new volume, which is just the combined volume of both solutions, to find that the new molarity of this solution will be 0.005 molar hydrochloric acid. Now, titration uses this idea of neutralization reactions to determine the molarity of a given acid or base. Imagine there's a beaker filled with 100 milliliters of hydrochloric acid at an unknown molarity. In neutralization reactions, we need to know the volume and molarity of a base that will neutralize that. Titration is the process of adding base one drop at a time until the solution becomes fully neutralized. Adding the base slowly is the key to titration, as the volume of the base that was added and its molarity give the information needed to calculate the molarity of the acid. The most difficult part about titrating is determining when a solution is completely neutral. This can be done by using pH indicators. Pictured is the indicator phenolphthalein. In an acid, the indicator is clear. However, in a base, the indicator becomes pink. The more basic a solution is, the pinker the indicator will become. While titrating, if this indicator is added, the solution will start appearing pink once it is neutralized. If the titration stops at that exact moment, then the requisite data we need to determine the molarity of the acid is obtained. Now, with all that understanding of acid-base chemistry, the proof that Tums is the best antacid can finally be uncovered. Antacids utilize neutralization reactions to combat stomach acid, which is hydrochloric acid when it is in the esophagus. And that is what causes heartburn. The chemical reaction picture, shown here, details how some of these antacids work. Specifically, Tums has calcium carbonate. When calcium carbonate is introduced to hydrogen ions, two hydrogen combine with the carbon trioxide part to create carbonic acid, as can be seen here. And then that carbonic acid breaks down into water and carbon dioxide. To prove that Tums is the best antacid, it will be compared to two other antacids, Alka-Seltzer and Gelusil. The claim of an antacid is that it is the best at neutralizing acid. The easiest way to test this is to add the antacid to an acid. In this case, it will be hydrochloric acid. To start, add and record the mass of around 0.1 grams of powdered antacid into an Erlenmeyer flask. Next, add and record the volume and molarity of around 15 milliliters of hydrochloric acid into the flask from a burette. Lightly swirl the flask to help dissolve the antacid into hydrochloric acid, and then boil that solution for 2 minutes. This should ensure that no carbon dioxide remains so that the reaction cannot happen in reverse. The next step is to prepare the titration. Begin by adding 4 drops of the indicator to the flask. Next, place the flask underneath a burette of sodium hydroxide. Be sure to record the starting volume and molarity of the solution in the burette. From here, slowly drip in the sodium hydroxide until a single drop changes the solution from clear to slightly pink. It's very important that it's just 1 drop because that is the data that we need. Throughout, consistently swirl to ensure that the base is evenly spread throughout the solution. Once the solution is neutralized, record the final volume of the sodium hydroxide in the burette. Here is that entire procedure written out, if that is important to you. The challenge now is to interpret this data in order to find out which antacid performed the best. The ultimate goal of this is to calculate how many moles of acid can be neutralized by 1 gram of the antacid. To show how this can be done, let's run through the first Tums trial. To find the moles neutralized per gram, the amount of antacid that the acid neutralized must be known. The first step to finding this is to find the number of moles of acid and base that were used. This can be done by multiplying the molarity of both solutions by its volume in liters. To find the number of milliliters used, the initial volume in the burette is subtracted from the final volume for each solution, which as can be seen is done here. And then that value is divided by 1,000, because there is 1,000 milliliters in 1 liter, to find the number of liters of both solutions that were used. In this case, there was 0.01479 liters of hydrochloric acid used, and 0.00064 liters of sodium hydroxide used. Then, the molarity is multiplied by the volume to determine the number of moles that were used. So in this case, molarity times volume equals moles. And that is done twice. There were 8.0 times 10 to the negative 4 moles of hydrochloric acid and 1.9 times 10 to the negative 5 moles of sodium hydroxide. Next, the molar ratio of the sodium hydroxide and hydrochloric acid can be used to determine how many moles the sodium hydroxide neutralized. Since there is a 1-to-1 ratio, these values are the same. The number of moles neutralized by the sodium hydroxide is then subtracted from the number of moles of total hydrochloric acid to find the number of moles that the antacid neutralized. So in this case, 8.0 times 10 to the negative 4, which is the number of moles of hydrochloric acid, subtract 1.9 times 10 to the negative 5, which is the number of moles that the sodium hydroxide neutralized, equals 7.81 times 10 to the negative 4 moles of hydrochloric acid. Finally, this value is divided by the grams of antacid used to find the number of moles of acid 1 gram of the antacid will neutralize, which in this case was 1/100th of a mole. With this data, the antacids can be compared to judge their effectiveness. Each antacid had 3 trials to ensure better accuracy. The reason why multiple trials is important can be seen in this data. The first 2 Tums trials are consistent. The first one had a moles neutralized per gram of 0.0097. The second trial had 0.0092. However, the third trial was somewhat of an outlier at 0.0061. This is likely due to human error. Perhaps I wasn't careful enough in doing the 1 drop. Perhaps I didn't boil it long enough. Because it is a significant outlier, we can just discard it. When discarding the third trial, the data averages out around 0.0095 moles per gram. For Alka-Seltzer, all the trials were done well, and the average moles of acid neutralized per gram of this antacid was 0.0029. Finally, the Gelusil antacid averaged around 0.0043 moles per gram. So the numbers here do tell an objective story. Tums neutralizes the most acid per gram of antacid, and it more than doubles the second place finisher being Gelusil. And this does work with the underlying chemistry. The antacids in Alka-Seltzer are sodium bicarbonate and anhydrous citric acid. These react together to create sodium citrate, along with carbon dioxide and water. The sodium citrate breaks down into its 2 ions, a sodium ion and the citric acid ion. This citric acid ion wants to be neutrally charged, so it combines with 3 other hydrogen ions to create citric acid before breaking down into carbon dioxide and water. This entire process is detailed here, so as it can be seen, sodium bicarbonate combines with the citric acid and 3 hydrogen ions to ultimately just dissolve into carbon dioxide and water. So what's important to know about this is that for every 3 moles of sodium bicarbonate and 1 mole of citric acid, 3 moles of hydrogen are neutralized. Using stoichiometry and the given number of grams for each reactant as detailed on the box, it can be seen that 1 gram of Alka-Seltzer's active ingredients will neutralize 0.00481 moles of hydrogen under perfect circumstances. The antacids in Gelusil are decidedly simpler. The active antacids are aluminum hydroxide and magnesium hydroxide. Both utilize the familiar hydroxides to neutralize hydrogen ions. The aluminum neutralizes 3 hydrogen ions per 1 mole, while the magnesium neutralizes 2. Again, stoichiometry and the number of grams of each antacid on the box can be used to determine that this antacid will neutralize 0.0344 moles of hydrogen per gram of its antacids. The chemical processes of Tums have already been detailed. However, here it is again for a little bit of a review. The calcium carbonate combines with 1 hydrogen ion to create carbonic acid, and then that carbonic acid combines with another hydrogen ion to become neutral. Finally, this breaks into carbon dioxide and water. So it's important to note that for every 1 mole of antacid, 2 moles of hydrogen are neutralized. Finally, one more time, using stoichiometry and the given number of grams on the box, it can be seen that 1 gram of Tums will neutralize 0.01998 moles of hydrogen, again under perfect circumstances. At first glance, the Gelusil is the clear victor, beating out Tums by a whole 0.015 moles per gram. However, this is only considering the moles per gram of active ingredient. There are more in antacids than just those active ingredients. There are binders, there are the things that make them taste like mint, and other substances that are not active ingredients, but do contribute to the number of grams. While the active ingredient in Tums may not neutralize as much acid per gram as Gelusil, there is significantly more antacid in 1 gram of Tums than there is in 1 gram of Gelusil, which makes it come out as the much better antacid. So the evidence has been laid out clear. Tums is the best antacid. Both in the lab and in the stoichiometry, Tums was shown to be the best at neutralizing acid because of its high concentration of the active ingredient calcium carbonate. So the next time your tummy gets a little rumbly, reach for Tums. And now with the sponsor segment out of the way, let's get back to the top 10 Fortnite funny moments. The number one I call One Health. That's because, as can be seen in this video, this guy's on 1 health. And this other guy is trying to kill him. They're just really trying to kill him. But he just can't do it. And then he gets the guy with a spike trap and lives on 1 health. That's pretty funny. Next, we have the Deadly Tumble. This guy, he's just having a good time building like you do in the game Fortnite. He puts some campfires down to help him regain some health. But then the storm comes and the platform disappears from out under him and he falls and dies. The third one is car theft. This dude balls in on his glider and kills these dudes who are driving the car and steals their car. That's Grand Theft Auto. Yes, sir. Next, we have the conga line. This guy here found a group of unaffiliated Fortnite gamers doing in a conga line, and then he decided to join them. But then someone tried to kill them all, and that did not end well because they all ganged up on that dude. Number 6 is Guitar Man. This dude, he knew that the game was over. He was outnumbered 1-4. So he started dancing for his captors, and they decided to kill him in the most hilarious way. Watch. Next, this dude in this one says, and I quote, I don't need no building. But then he gets immediately shot and killed right after that. Next up, we have this dude. He had to go pee in real life. So he dropped his Fortnite character and let them just chill in a bathroom while he went to the bathroom. But his opponent died in the storm, which gave him the victory royale. Next, this dude right here just kept saying Star Wars references, and he wouldn't stop. He would not stop saying Star Wars references. And that's funny. That's really funny. This one I call He Was AFK, because this streamer found an AFK guy and started to make a nature documentary about him. Final one is the rescue mission. This dude found this guy stranded below the build limit. He couldn't build himself out. So he decided it's rescue time. So he gets a golf cart and crushes him with it, killing him. Well, that's been the top 10 Fortnite funny moments. If you enjoyed the video, make sure to leave a like. And if you really loved it, make sure to subscribe and ring that notification bell. I've been Chucky Hats. See you later, alligator.